Hello, and welcome to topic 4, the lecture for part 4. This is the final lecture in topic 4, which is your reaction section of the summer assignment. So this one is all about double replacement reactions. Most of this will be review for you. There will be a little bit that is not. So make sure that you're paying really close attention to catch on to those things that I introduced that might be new to you, and get a really good foundation so that we can build on what you already know. You should have already completed these learning targets. They're a little bit longer than the last few have been. So please make sure that you use the packet to make your definitions and to start to look at solubility rules. Make sure that you already know the kinds of things that you're looking for that would create a double replacement reaction. That would mean that ions are coming out of solution and sticking together. This is really what a double replacement reaction is. So make sure that you have all that idea. There is a fair amount of information to memorize in here. You should be memorizing your always solubles and your 6 strong acids and your 6 strong bases. I also already hinted for you at the definition of acid and base anhydrides. That was from the synthesis and decomposition lecture. So if you need to go back and watch that because you can't figure it out from what you're seeing here, then definitely maybe go back and watch that before you keep going. Okay, hopefully your learning targets are set and ready to go. Let's see what we can do. Remember to add to what you've already built. All right, so double replacement reactions are really the reactions between 2 solutions, and they're the reactions between the ions in those 2 solutions. So because it's 2 ionic compounds, really what you have is 4 ions in solution, and if those ions stay dissolved, then you have no reaction. So what you're looking for to create products, to mean that you have a double replacement reaction, is something in which I say the ions stick together. In other words, there are a few things that will make those ions not be a part of the soluble ions anymore, that will make them not still be dissolved in the water of solution. So there's 3 categories of this basically, and you kind of will start looking for each one of them separately. We have reactions that are what we call precipitation reactions, which means they form an insoluble solid. All right, and we'll talk about that a little bit more in a minute. We have reactions that form gases. These gases might be the product of a decomposition. Like, remember, we might form H2CO3, which then decomposes into, you know this already from your decomposition rules, water and carbon dioxide. And that carbon dioxide and water, those are molecules. The carbon dioxide is a gas. So that means that in this case, the H plus ions and the CO3 2 minus ions that would have been floating around are no longer in solution. They're a part of this. And so that's creating a reaction. We also could form other molecules. We might form just water. Or we might form weak acids, and those would be molecules. So we're going to explore each of these in a little bit more depth as we look at this whole topic, at this part of this topic, but I definitely want you to have an idea of what's coming. So what you see here, I really like visuals. I love the pictures, I love the images, and I really am wanting you to be thinking particle level. All year long, the more that you can think about particle level, the easier the conceptual piece of this course will be for you. So in this case, what we really have here is not copper 2 sulfate like this is, but rather we have copper 2 ions and sulfate ions, because in our solution. And over here, what we have is really sodium ions and hydroxide ions all floating around in water. So it's kind of misleading to think of those as compounds. They would have been compounds before we dissolved them. But once they're dissolved in solution, now we have those ions. And then over here, what we have is this sodium sulfate that they're saying is still in solution, which is really then sodium ions and sulfate ions. And what we have is the copper 2 hydroxide solid that would have formed throughout and then settled to the bottom as a precipitate. So the fact that the copper ions and the hydroxide ions stuck together mean that this is a reaction. So that would be the precipitation option. The gas forming, you're always on the lookout for the formation of three things. And so I'll address those in just a second, but you can see that in this case, we would have taken this acetic acid, which I would not have written the formula like that. I would have written it as CH3COOH or as HC2H3O2 so that you could see the hydrogen ion that's going to be replaced. And then you have sodium bicarbonate. So what happens is that the sodium and the hydrogen switch places, leaving you with sodium acetate and H2CO3, which then decomposes into water and carbon dioxide. I like this because in a minute I'll show you, you can definitely see how that H2CO3 structure would allow that to occur. Okay, so we'll do it with ammonium hydroxide and I'll show you that. And then finally, the last option here is forming the molecule of water. So what's happening here is that this would still be dissolved, right? The NaCl would still be dissolved. So we'd have NaOH and HCl, and what happens is the H and the OH combine to form water. And that's really what we call an acid-base neutralization, but it forms that weak, or that molecule, which then means that the hydrogen ions and the hydroxide ions are not still dissolved in the water. So this is how we look at this. So let's see what we can do. The first thing that you're going to look at specifically is whether or not you would form a precipitate. And the only way to do that is to know your solubility rules. For right now, it's enough to memorize the always. All right? So you should be memorizing that all nitrates are soluble, all acetates are soluble. Don't even worry about the exception right now. All chlorates are soluble. You should also be remembering that all alkali metals and ammonium compounds are soluble. So remember, this is group 1A. So this is lithium, sodium, potassium, etc. Okay, and we're talking about the ions in solution. This means that in solution they will never combine. All of those are the only ones that are always soluble, okay, except for your H plus ion when it's in a strong acid. These are also considered to be always soluble. Okay, so your strong acids and your strong bases are always soluble. So I would really like you to memorize those things. You should be memorizing the 6 strong acids as 100% soluble. You should be memorizing the 6 strong bases as 100% soluble. And you should be memorizing group 1A and ammonium, nitrate, acetate, chlorate. All right, so that's important. After that, you have to read carefully to decide if compounds are soluble or not. So we can look at this as we're looking and see what's happening here. The reaction that I have this picture of here would be lead iodide and, would be maybe lead nitrate, potassium nitrate. No. Potassium chloride or potassium iodide and lead to nitrate. Okay, so one of these would be in the top beaker, one would be in the other beaker. Notice that they're both clear and colorless and definitely dissolved. Remember that clear means dissolved or soluble and cloudy means insoluble or not dissolved. So anytime something's cloudy, you're actually seeing the particles. And the particles are big enough to see, which means they're not dissolved. Okay, so we start with these 2 solutions and we pour them together, and you can see right away this getting cloudy and getting cloudy. And if I stirred this, instead of just pouring it in there, I think it's kind of cool, you can see all those little layers in there, but if I stirred this while I was pouring, it would just be cloudy. It would look like yellow milk. All right, and then eventually when I let it sit, it would settle to the bottom and you'd have a clear colorless layer up above. All right, this is why we call it a precipitate. And so it precipitates. Remember, we use precipitation in weather. It's things that fall from the sky. So you can picture that your precipitate is your solid that falls out of the liquid of solution. And this is because two of those ions stuck together. So in the example that I have here, the solution up here would be the potassium nitrate, which would still be dissolved as potassium ions and nitrate ions, because all group 1A, potassium is group 1A, or all nitrates are soluble. I don't even go past the group 1A. You should always start with this. Okay, and so the solution above here would be potassium and nitrate, and this down here would be lead 2 iodide. And I know that because I can come in here and find iodides and see that lead iodide, all iodides are soluble except, so lead iodide is insoluble. I can do the same thing here with sodium chloride and silver nitrate. I have all 4 ions floating around. I pour them together. The silver and chloride ions stick together and form the solid, eventually settle to the bottom, and the sodium and nitrate ions would stay dissolved. And I know that it's the silver chloride sitting at the bottom because of this rule. And of course, because sodium is group 1A, the sodium and the nitrate will stay dissolved. So that's how you do precipitation. College Board has said in the past that you don't need your solubility rules memorized, but they do enough questioning about things that I think the only way you can figure it out is from solubility rules, that I think it's important that you know them. Okay, the second type is the formation of a gas. You have to be watching for these. H2S is it's gonna feel like a molecule to you, but this is the stinky rotten egg gas that is in stink bombs. H2CO3 will form water and carbon dioxide. H2SO3 will form water and sulfur dioxide. And NH4OH will form water and NH3. And so right away, as soon as those stick together, these molecules actually decompose again, and this is what's causing our reaction. So if it's going to be CO2 or SO2, you'd actually see bubbles in the lab. If it's going to be NH3, the bubbles are too small, the same with H2S, but you can definitely tell they're there because of their odor. So ammonia is cleaning solvent or cleaning solution, and so most of you will know what that smells like. We'll do this in the labs at some point so that you'll be able to smell it. I do want you to see how this works. Really what we would have would be 2 separate ions. As soon as I dissolve this in water, the NH4 plus ion and the Cl minus ion would separate from each other. And the sodium ion and the hydroxide ion would separate from each other. And then all of these 4 things would be floating around in a beaker, and the ammonium and the hydroxide definitely would attach to each other. This is forming this big molecule, ammonium hydroxide. And even though your solubility rules say all ammonium compounds are soluble, not NH4OH, because it decomposes, so it doesn't have a chance to redissolve. Okay, and then of course this would still be dissolved, and so this would be the 1 plus and the 1 minus, and we would actually have this still in solution. But this, you can see right here how as soon as this attraction forms here, now all of a sudden this portion would be very easy to pull off from this portion. And what we end up with is those 2 molecules. So you are on the lookout for the formation of these compounds because they will mean that a double replacement reaction has occurred. And if it's these 3, then you have to remember that you get water plus what they decompose into. All right, the final one is a little bit more complicated. This would be the formation of a molecule. The molecule could be water or a weak acid. So from your strong acid list, all acids that are not strong are considered to be weak. And what this really means is that they stay as molecules. Rather than dissolving into ions, they stay as molecules. All right, and so these guys, the strong ones, will dissolve into ions, but the weak ones stay molecules. So the formation of that molecule takes those ions out of solution. And so we're looking for how this works. So we have 2 different ways that this happens. Water can be formed from an acid-base neutralization. Always an acid plus a base gives you water plus a salt. Acid plus base gives you water and a salt. Okay, and so what you're picturing here is that this salt is probably soluble. So it's not going to make the reaction occur, but the water will. You do have to be on the lookout for anhydrides because they might go in as a solid, but if you add them into something that is a solution, like potassium hydroxide or some other solution, the first thing that they're going to do is form the acid from the acid anhydride. Okay, so you definitely want to be watching for that the acid anhydride, if you're putting it into something that already has water in it, will form the acid. And the base anhydride, if you're putting it into something that's in solution that already has water, will form the base. The water does not become a part of your overall equation, but it's a part of the picture of what happens, and that will help you remember how this works. So I'm going to walk you through one because I do think they are kind of complicated. So sulfur trioxide is a non-metal oxide, which means that it is an acid anhydride. So when you write it in your equation, you're going to write it as SO3, but you have to picture as H2SO4. Okay, and the way that you know which acid it forms is because of the oxidation numbers. So you can guess and check. It would be either H2SO4 or H2SO3, and you can guess and check. In here, this is 6 plus. In here, this is 4 plus. In here, the sulfur is 6 plus. Okay, so we know that it's this one. So you want to picture that that's what's reacting with your potassium hydroxide. Potassium is K plus, hydroxide is OH minus, so this would be KOH. And this is complicated if you don't picture it as H2SO4. So the first thing I would do would be think of this as H2SO4. And in that case, now I can picture the double replacement reaction. So I would form hydrogen with hydroxide and potassium with sulfate. And hydrogen with hydroxide, I can write it as HOH or I can write it as H2O. Okay. Now, what's really weird is that the water is not a part of the reaction because it would just end up some of it canceling out again. Okay. So it's kind of strange that you picture this as H2SO4, but you only write the anhydride in the equation because you didn't put sulfuric acid in there, you only put sulfur trioxide in there. This is probably one of the most complicated things that we can do. All right, so you're going to write it the way it came, but you're going to picture it as the acid that it would turn into as soon as it's in solution. If these are two solids, this doesn't happen. But if this is an acid or a base anhydride with a solution of something else, it will. Okay, now I can come back and balance the equation with coefficients. So this would be 2 potassium, and I'm hoping that fixes everything else, but let's double check. So I have a sulfur and a sulfur. I have 3, 4, 5 oxygen. I have 4 and 1 more is 5. I have 2 hydrogen and 2 hydrogen. Okay, so you can see how this is kind of complicated. The other thing that I want to talk about then would be how you form weak acids. So the formation of a weak acid comes from the reaction of an acid with a compound that's not a base anhydride. Because if it's a base anhydride, then it's going to form a salt and water. Okay, so we are looking at the idea of an acid, maybe HCl, with maybe potassium. Nope, don't like that. Maybe I should have done this on my own first. Let's see. With maybe potassium nitrite. Okay? So now what happens is that when this reacts, we have HNO2 and KCl. The KCl, this is a group 1 metal, this is soluble, so it's not going to make the reaction occur. But this, remember on your strong acids, nitric acid is strong, but nitrous acid is weak. So because this is a weak acid, it stays together, and that means that I have a reaction. Okay, only one more thing here to talk about, and this would be how these different things that are soluble or insoluble as ions or as molecules act when we conduct electricity through solution. So electrolytes, you've heard this term because you're used to electrolytes from like Gatorade and things like that. But electrolytes by definition are things that conduct electricity in solution. All right, so if I dissolve something and it doesn't dissolve into ions, then it's not going to be an electrolyte. It doesn't mean it won't dissolve, because we have lots of things that are molecules that will dissolve, like weak acids, like sugar, things like that stay molecules when they dissolve but are still soluble in water. Okay, those would be non-electrolytes. So these do not conduct electricity. And this would be things that are soluble molecules, like sugar, or like ethanol, something that is polar, that will dissolve in water but does not turn into ions, and things that do not dissolve, like ionic compounds that do not dissolve, because if you have an ionic compound that doesn't dissolve, it's not going to be able to have the ions conduct electricity. You need ions in solution for electrical conductivity. Okay, strong electrolytes conduct electricity really well. Notice that this light bulb is glowing brightly compared to this light bulb, which is not glowing at all. Okay, so strong electrolytes would be your soluble ionic compounds and your strong acids and bases, because they ionize 100%. Okay, so they form lots of ions. So they conduct electricity really, really well. And then we have weak electrolytes, which are things like water, which actually more will come later this year about that. It's a really weak electrolyte. But mostly our weak electrolytes we think about are weak acids. And this is because they actually, even though we write them as molecules, ionize partially. Okay, so we'll talk that a lot more. A lot more comes with our weak electrolytes in our equilibrium unit, which is actually in the second half of the year. But I just wanted to introduce it to you now as you were thinking about what was happening. So a little bit of new stuff here on top of your old stuff for double replacement reactions. Work really hard at memorizing what you need to memorize and understanding what you need to understand, and practice. You have 3 sets of practice, I think, on the packet that go with double replacements. Make a list of things that you might have questions on and be ready to ask for help if you need it.